All right, I think we can go ahead and get started with this. Good afternoon. Hope everybody enjoyed their lunch. My name's Aaron Jones. I am part of the Epic team. I'm on the ECE team. And I'm kind of filling in on the MC role since we've had to split into several rooms right now. This session right now, if you're here for the UFS Global Applications Across Scales, you're in the right place. This is going to be chaired by Dr. Fenglin Yang. And then we can go ahead and get started. If you are a speaker at this session, pay attention to me. I'll have some cards and I'll kind of give you a rough idea what your time's at. It looks like everybody's going to have roughly 12 minutes to speak. If you're online, I'll try to jump in on the mic and just kind of give you a heads up, like tell you got 1 minute left or 3 minutes left so you know where you're at.
Well, thank you for coming to this session. To start, first I'd like to thank also Martin and BGM from PSL and Christina Stan from George Mason University for helping organize this session. It won't happen without their help. And not all work involved to get this session going. And also today, Mike Balaji was little questions. So we have a lot of good talks today, but UFS modeling development standards, physics development verification, even workflow, and also mid plus application. Without further ado, we'll start with the first speaker, Cassie Thomas on the GFS development. She's online.
Hello, everyone. Can you hear me?
We can hear you.
Okay. Hello, everyone. I'm Kathy Thomas. I'm in the Global Data Assimilation Group at EMC and currently serving as a co-lead for the GFS version 17 implementation. I'd like to acknowledge my co-authors, the other project leads for this project, as well as the many others who have contributed to this huge implementation. So the UFS, as well as the specific application of the GFS, wouldn't be possible without the many developers, not just from EMC, but also from NOAA Labs, Joint Center, and many others. And I'd also like to acknowledge the support that we receive from OSTI and the Program Office for this project. So the Global Forecast System, or the GFS, is the cornerstone of the NSAP production suite, providing initial and boundary conditions for much of the rest of the suite, including the Global Ensemble Forecast System, or the GEFS. So our current operational GFS, version 16, has an atmospheric horizontal resolution of 13 kilometers with 127 layers, and is one-way coupled with a wave model. It runs 4 times a day out to 16 days, and the data assimilation is performed at 25 kilometers with an 80-member ensemble and the same vertical resolution as the deterministic. Our next major implementation is version 17, and it will be a weakly coupled system with a coupled forecast model consisting of components for the atmosphere, land, ocean, sea ice, and waves. With new model components also comes new data assimilation components, and these will be implemented through the JEDI framework. As with many of our implementations moving forward, we continue to have an eye on consolidating the NSAP production suite, bringing GODAS into the GFS, while also making significant efforts to bring the GFS and the GEFS into greater alignment. We've taken a lot of care to consider the shortcomings of the current operational version and work towards addressing known issues such as underestimated CAPE and biases in the wave model. And of course, we're looking to improve on the existing atmospheric model with updated physics and increased horizontal resolution. So here's an overview of each component. As I mentioned, the atmosphere will be moving to 9 kilometers for the deterministic forecast, though the history file output will remain at the current 13 kilometers to reduce our disk footprint, also to reduce the burden on downstream users. And ensemble resolutions will remain unchanged at 25 kilometers, and the vertical resolution will also remain unchanged. The ocean and sea ice will be at a 1/4 degree resolution, and then the waves will also be introducing an unstructured grid. And then the previously planned predictive aerosol component will actually be moved outside of the GFS into the new GCAPS. Though the GFS will still utilize a climatological aerosol component for the radiation. So I mentioned how the new DA components were going to be using the JEDI framework. So while you've probably already heard this week, JEDI is the Joint Effort for Data Assimilation Integration, and it's a project in the Joint Center with contributions from many agencies, including Weather Service, NASA GMEO, UK Met Office, and others. It's a software infrastructure built with modern programming that is portable, flexible, and model agnostic. So our current DA infrastructure, the GSI, is reaching its limits of scalability, and then with new DA components on the horizon, with a move to couple modeling and assimilation, NSEP committed to using JEDI as a unified data assimilation framework moving forward. So for the V17 implementation, we will be using JEDI with our ocean and sea ice DA and snow DA, with aerosol DA and atmospheric DA being transitioned in other systems and future implementations. So for version 17, we'll be implementing a weakly coupled system, meaning that the forecast model is coupled, but the DA for each component is performed separately. So as I mentioned, the atmospheric DA will remain GSI for now, and we'll use this implementation to upgrade it to a multi-scale algorithm with scale-dependent localization, and also include an additional early cycle ENKF analysis to initialize the GEFs more consistently. The marine DA will be done using the JEDI-based SOCA and will be strongly coupled between the ocean and the sea ice. So meaning the DA for those two components will be performed simultaneously. And we'll be introducing new land DA components with a JEDI-based 2D VAR for snow, and then strongly coupling the soil states with the atmosphere within the GSI-based LATTF. And then, as mentioned for the aerosol DA that was previously planned for GFS V17 has been moved to GCAPS. So the UFS R2O project diligently worked through several forecast prototypes of increasing complexity and resolution to build out and tune the coupled model. So this is prototypes P1 through P8 that you've heard throughout the week. When we started moving from UFS R to O to GFS T to O, we moved to the HR, or high resolution prototypes, using all of the findings from the previous set of prototypes to inform the starting point of the HR runs. In parallel, we also continue to integrate and test the new DA for the non-atmospheric components in lower resolution cycling prototypes. So now we moved to full integration of the planned system at the target resolution. So the following slides aren't really meant to be comprehensive evaluation of V17 in comparison to operations, but will highlight some of the previous and ongoing prototype and evaluation activities. The HR prototypes were free forecast runs at the full resolution, including a couple components of atmosphere, ocean, sea ice, and waves. And these prototypes were iterative with wide-ranging evaluations, looking at things such as CAPE on the right, where you can see the increase in CAPE from HR1 to HR2. Along the bottom, you can also see the effect of some changes in surface properties from HR1 to HR2. With the difference plot of shortwave radiation on the far right, here you can see improvement, particularly over Northern Africa, where there was a strong bias in the earlier prototype. Here are some other highlights from the more recent HR runs. So on the left, we have an evaluation of the structure of tropical cyclones with HR4 on the far left. So it's showing reasonable wind structures for tropical cyclones, though we have some biases near the core. You can see that are slightly increased compared to operations, which is on the right. But then on the far right, we have a bulk statistics scorecard for HR5 compared to the prototype before at HR4. Have Northern Hemisphere summer on the top and then winter on the bottom. You can see different variables and vertical levels along the y-axis with different regions and forecast lead times along the x. So we can see some improvements in short lead times for HR5 when we compare to the previous HR4. where we made some changes to the orographic gravity wave drag and some land physics and cloud radiation interaction changes as well. So in parallel with the high resolution free forecast prototypes, we also ran multiple low resolution cycling prototypes. And that was focusing on the impact of each new DA component. And then from there, we also ran some full resolution infrastructure tests, and now we're evaluating the science and performance of the full resolution cycling prototypes for the target system with all components included. So for these low resolution prototypes, as I mentioned, the atmospheric DA now includes a multi-scale component with scale-dependent localization utilizing 3 scales. And this work was done in collaboration with Shoyu Koda, a visiting scientist from JMA, and the OU MAP group. And then with this localization, we see the most improvement in the upper layers, pointing to likely suboptimal tuning in our previous system. But then moving to the marine side, you also see, so the results when including sea ice and ocean DA have been looking quite reasonable, and you can see here for SST, thank you. Our marine DA case in the pink is shown closer to Ossia than the replay in the black. The land DA side also produces quite encouraging results when isolating soil and snow DA and gives positive results where we expect, namely low level temperature and moisture. Comparisons against aircraft data on the left. And then we also have comparisons of self-analysis out to 10 days for 1,000 hectopascal temperature on the right. You can hear more about these in the other parallel session in about an hour. So we are cycling the target system with all components included at full resolution. We still have some areas of concern and continue to tweak the system. You can see on the left we have 2 candidate runs with small changes between them in the land and convective clouds. The right shows the scorecard of the red line compared to operations, where we're seeing statistically significant improvement in the shorter lead times. But of course, we're taking a closer look at this Northern Hemisphere winter time period with the longer lead times. And just one small closer look at some of the difference between that red and green line in the previous slide, these 2 candidates. We saw a large bias over Antarctica in the upper right panel that we mitigated by making some changes to the snow albedo. And then you can see here on the right, comparing those 2 candidates directly, the updates have provided statistically significant improvements in the Southern Hemisphere. And I will leave up my summary slide here for you to read yourselves. Thank you.
In the interest of time, we'll move on to the next talk. Maybe that there are questions on the Slido and try to answer that so that we can. Our next speaker, you want the next one?
Yeah, while the next speaker is coming up, Kathy, can you check the Slido? There is a question for you.
Sure, I'll do that. Thank you.
So next speaker, before report the status of the GFS version 13 development.
Afternoon, everyone. Can you see my screen? I assume you can hear me and see my screen. If not, you just stop me and let me
Yes,
know.
we can.
Okay, great. Thank you. Good afternoon, everyone. I'm very happy to be here to give you some updates about GAPS Version 13 project. I'm Bing Fu from EMC. I'm currently co-leading this GAPS Version 13 project with Neil. And yeah, before I start, I also want to acknowledge all the contributions from GAPS, GFS, and the GAPS model developers at EMC and also in the UIFS model community, because it's a big project from all the contributions from others. Yeah, here is the outline. Today I'm going to first.
Could you please speak up a little bit more?
Okay. I'm going to give a brief review of GAPS Version 13 development. Then I'm going to show some results from the most recent experiments And also I'm going to show some challenges and the future plan for GAPS version 13. Just to try to refresh your mind about GAPS version 13, the upgrade from version 12, current operational. This is model configuration. Actually, I showed this figure, this table last year in this UIFCW meeting. And you can see the table on the right is version 13 configuration. We have a lot of updates, like Cassie already talked about this early in-cab initialization, and also a lot of physics updates. We doubled vertical resolution for atmosphere model and updated land surface model. And I think a major update, we update the model from uncoupled model to fully coupled model, including two-way coupling, ocean, ice components, and also two-way coupling wave. But one difference compared with last year's presentation is for the aerosol component, we have made a decision. We are going to exclude aerosol in the GAPS version 13 because we have a new model. It's called the GCAPS. We cover aerosol component. I hope, also Cassie also mentioned this is a new model. I hope Barry is here in the workshop. I can hear you present something related to GCAPS. This is the ensemble prototypes for GAPS version 13 because we, during the development, we have, actually we follow the UFS coupled model prototypes. We developed the corresponding ensemble prototypes. So far, we have 6 ensemble prototypes. You can see here on the left, you see the EP1, the first ensemble prototype based on P5, and the latest one is EP6, based on HR4 prototype. And also, you see here EP4 and EP5, we just start here. These 2 ensemble prototypes have aerosol component, two-way coupling included. And because we have made a decision, we are going to exclude aerosol component. So the latest one, EP6, does not have aerosol component, the go-kart model component. And this EP6 also the current reforecast configuration. Some results from our prototypes. This is EP5R2. This is previous ensemble prototype. I showed this figure last year, just to try to refresh your mind. This is just comparison between current operational GAPS version 12 and EP5R2. This is the current operational GAPS version 12 in black and EP5R2 in red. You can see clearly this EP5R2 has a lot of improvement in terms of this 500 bar high CRPS scale for both northern hemisphere on the left and the southern hemisphere on the right. It's consistent performs better. This EP6 is the current reforecast. You can see this is comparison only between EP6 and EP5R2. You already see from previous slide, EP5R2 is better than current operational GAPS. And if you see the comparison between EP5R2 and the current EP6, this EP6 has, again, slightly improved this 500 millimeter height AC score here, especially for the 2 to 3 weeks. You see here, in the northern hemisphere, for the first 2 weeks, it's also statistical significant improvement. See here, but on the right is southern hemisphere. You still see the improvement, but it's not statistical significant. This is model biases. On the left is the northern hemisphere, on the right is southern hemisphere. This is the profile for the temperature, the bias. So generally you can see on the upper level, you see the newer model, this EP6, compared with previous ensemble prototype EP5R2, we have reduce these code biases. Compare this, you see here, reduce the code biases. But if you see the middle to lower level, you see the warm bias also has increased. You see, it's more warm. It's warmer, and also same thing in the southern hemisphere. We can see you can reduce the cold bias at an upper level, but we increase the warm bias in the lower level. This is another highlight for EP6 compared with previous EP5R2. This is the RMSE for lower on the left and upper on the right. So the wind. This is left is the 850 millibar wind RMSE. So you can see EP6 compared with EP5R2, we have significantly reduced RMSE for tropical wind for both lower level and upper level. You see on the 200 millibar on the right. These figures actually from CPC. They help us evaluate the for week 1 to week 4 the precipitation and also to meet the temperature.
Got 3 minutes.
Thank you. So on the top is biases, and the RMS is on the bottom. You see for EP6 and also EP5R2, you can see the bias has been reduced, and also for both precipitation, also to meet the temperature, but it's still not as good as European Center. But it's definitely it's better than current operational gaps. And we also have some challenges for current reforecast. We found some issues from the current reforecast. We had some model crashes because of this because we have inconsistent surface initial conditions. The replay initial conditions from HR1 model is an older model, and we are running HR4 model. So got this grid mismatch is causing the model crashes. And we also found a bug in wave input file. We accidentally had this stock drift not turned on. And another is we also found degraded MGO skills and some other bugs in the model code. Another challenge is for future optional GFS version 17, we'll be using a newer version model. It's not HR4, it's HR5 plus. So there's going to have discrepancy between GAPS version 13 and GFS version 17. And in the meantime, we recently we have changed the GAPS version 13 implementation plan. Originally, we are trying to implement GAPS version 13 and GFS version 17 at the same time. But right now, we are going to implement GAPS version 13 after GFS version 17. So we get more time. That's a reason. That's one of the reasons we have updated the plan for reforecast. We are going to use the latest model with all the bug fixes, and we're going to switch to using surface initial condition directly from new spin-up with no DA. And we have some benefit to with this. We can avoid model crash due to the inconsistent service IC, and the reforecast will be consistent with operational gaps and the GFS version 17. This some results. We have bug fix, improved this the model biases. This is so the temperature at 850 millibar on the northern and southern hemisphere. And also the latest model shows improved precipitation and OLR to expect the MGO skill will be improved a little bit. So here's the takeaway, some takeaway message. So aerosol component will be excluded in the GAPS version 13. The current reforecast is comparable in general with previous ensemble prototype. Some highlights include slightly improved AC score and reduced RMSE, and we have some issues in current reforecast. As GAPS version 13 implementation plan has changed, we updated plan for GAPS version 13 reforecast by switching to a newer version model to be consistent with the original GAPS version 13 and also GFS version 17. I'll stop here. Thank you.
Thank you, Bin. And for all speakers, try to keep your talk in 10 minutes if possible. So we'll move on to the next talk by Phil Pigeon from PSCR. Longer time scale now is a seasonal forecast system, still under UFS.
All right, so yeah, I'm talking about the longer time scale application of the seasonal forecast system, which is not as it's not as mature. And what happened there? Okay, so this is a talk about now because my co-authors are Neil Barton and Kate Zhu from EMC. From PSL. The three of us are the co-leads for the seasonal forecast system development team. And the introduction here, because maybe everybody's not familiar with the seasonal forecast system because it's a newer project. It will be a global couple application of the UFS, just like GEFS and GFS. But the main difference is the forecast time leads. This sort of provide ensemble forecast guidance out to 12 months lead time. And to support those forecasts, a 40-year set of retrospective forecasts will be run for forecast calibration and bias correction. And then briefly talking about the development team, so we're in the second year of developing the seasonal forecast system. We're almost at the end of the second year. Third year, we're starting in October. And this will, okay, what happened? Why did it go away? Oh, okay. Thanks. So the intention is to replace the climate forecast forecast system version 2 by 2028. This project is funded jointly by the Weather Program Office and STI modeling programs. And the development team spans multiple centers, EMC and CPC mostly, multiple OAR labs, and then also several research universities, and also DTC. And the teams now have three main focus areas. One is the model development, which includes atmosphere, land, ocean, sea ice development, ensembles, forecast products, and the infrastructure. And then there's a second focus area on evaluations of our experimental forecasts and initial conditions, and developing evaluation tools that will help support the model development teams. And then the third focus area is the data simulation and reanalysis. And sort of quickly summarizing the progress over the last year, we've carried out many experiments, many short sensitivity experiments, which I'm not talking about here, but then we've done a handful of full sets of what we call phase 1 experiments, where we're doing retrospective forecasts for 30 years, 11-member ensembles, and multiple initializations a year. And there's also been various publications, and one I'm going to highlight here is from Shan Sun that was accepted this summer, that looking at the importance of the ocean initialization in ENSO predictions for the trade-off of accuracy of these initial conditions versus the consistency with the model. And there's been lots of efforts on physics improvements in tuning, and I'm sure you'll hear more of that later in this specific physics talks. And then also looking at the dependency on the model resolution. And what I just want to show here is that as we're running these forecasts, we've been processing monthly means and putting them up on an AWS bucket through NOAA's NOD. And this QR code will point you to that data. And there's ocean and atmospheric output in ZAR format for anybody to look at. So then just a quick summary of the reforecast that I can present here. There's 4 different experiments, and where they differ in initial conditions, in the version of the model, and then also in resolution. And this is just details here. The first baseline that we did was only out to 4 months, and then we learned quickly that we want to run these forecasts longer because we're seeing growing biases and whatnot. So then every subsequent experiment has been 12 months in length. And quickly on the left is a comparison of the Nino 3.4 forecast scale for our two initial forecasts, the top two, I'm going, how do I go back? The top two forecasts here, which is for this, it's considered the HR4 version of the model, and I'm going wrong place here, sorry. And what I did is I compared from 1994 to 2016, that's what I had for the common period, compared to CFS2 and to SPEAR models. And first thing is this CFS2 is the blue line that even out off the month 1, the CFS2 is having initialization problems, has poor skill. SPEAR does better at initialization, but the forecast skill degrades pretty quickly, whereas the two versions of the SFS that we run are doing pretty good. And see here, the red line is initializing with the CPC initial conditions, is actually pretty good skill until it hits the spring barrier the next spring. And then on the right is now those 4 experiments I showed, and quickly, again, at this, which one's the laser pointer? The top one? Okay, thanks. Okay, I got to do it here. Okay. So you can see that this red line with the CPC initializations is the highest forecast scale for many initializations, but the point also is that all of these are pretty close. If I put error bars on here, I don't think there would be overlap. And then also on the show, because we're trying to understand why is the forecast degrading between these two. So then I looked at individual years, and now I'm just comparing the difference. It's the same model, so it's the same initial conditions. It both has CPC initial conditions. The only difference is the version of the model, and that's the black line is the the beta version of the model, ensemble mean, and this is for each of the 30 years. And then blue is the newer version of the model, and then red is verification. And if you look here, the lines are falling up on top of each other. There's just a couple of cases, like here, like 1998. You see there's a slight difference in the ensemble means. And so again, I don't think this difference is significant. I know developers are worried about it, but the bigger problem is if you look at the ensemble spread, it's way too big. So this is the next thing that we're kind of trying to tackle is, like for the case of 1998, you can see the ensemble members are ranging from, it's like almost -4 Celsius to like a +2. So you could go from like a record-breaking La Nina to a strong El Nino, depending on each ensemble member. So good thing is that we've discovered how we could tune this, and we're working on that now. So we're really not going to be digging into that forecast skill so much until we could get a reasonably calibrated ensemble. And then this is just a map of the 2-meter temperature scale for the first lead for season. And there's a typo in here. This is really May, June, July seasonal mean, not June, July, August. So I guess, and then the top row is the baseline model. Bottom row is the beta version. So if you compare the top left and right, that's the different initial conditions. And if you compare the bottom left and right, that's the change in resolution. So in this sense, you don't really see much change in resolution. You see a difference in the forecast scale going from the initial conditions, mainly in the southern hemisphere, like over South America and Australia. We're going from baseline, from the replay initial conditions, which is the same ones that GFS version 13 are using, to the CPC initial conditions that you see the degradation there. That carries on into the new models, and we're looking into these things right now. And then this is another ongoing issue that we've had, and making great progress on it, is the warm bias that we have in the sea surface temperatures in the mid to high latitudes in the summer. So what I'm showing here again is this May initialization. So this is valid June, July, August, and you can see in the northern hemisphere, the oceans are warm pretty much everywhere. And in the beta version, which is the next row, it's a slight improvement. It's still too warm though. Thank you. So then I'll just summarize with the next steps here is that we're continuing to develop the model to reduce the biases, and like I mentioned, improve the ensemble spread, and looking at the forecast skill. And then going forward to operational implementation, where we're going to be running this operationally most likely with the GFS 17 initial conditions, we need to have a consistent reforecast data set. And so we're going to be looking at testing reforecast with the GFS 17 initial conditions when they're ready, compare them to different candidates for the reforecast, which would be a reanalysis that PSL is leading, and you'll see more about that later today, I think. Zhao will be presenting that. And then there's also, again, we're going to compare the CPC initial conditions. Since the current version of the SFS is substantially better than the CFS version 2, EMC is looking to basically create a near real-time version of this beta system that will be run not efficiently operational, but will still be producing, real-time forecasts that CPC and others could use. And in this beta version, we'll create reforecasts on the fly, which will allow us to, maybe in 6 months we have a better version. We could switch to that one in real time, run the reforecast, and then not have to wait for a full reforecast data set. So I'll leave it there if there's any questions, if there's time.
Thanks. Probably we can take one question. Thank you for finishing. Another question or not?
Or he's running away. Okay.
Then we'll move on to the next one.
Sure. All right.
We'll have limited time. So the next speaker will be Justin Parkett from GFDR, talking about the installation of the GFDR land model in phase 3 and UFS.
Like you said, I'll be talking about the efforts of porting the GFDL land model into UFS, including the two-way coupling. So the GFDL land model has a couple of versions in use. Version 4.0 is employed in SPEAR, as well as the couple physics model version 4. Among many above ground, below ground, radiation, energy, hydrology representations that it shares with other land surface models. It features a truly dynamic vegetation with carbon growth, integrated fire model, forestry, harvesting, and crop model. It also has within it an integrated multi-layer lake model and river model. The rivers not only route from grid cell to grid cell across the land surface, but they also have their own surface fraction, so they have their own surface exchange with the atmosphere. There's also a glacier representation as well. There's a newer release version, LM4.1, that has even more advanced ecosystem representation, plant succession, hydrology that's used in Earth System Model version 4.1. There's also currently newer in development version, but this project focuses on LM 4.0. It's a bit less expensive than 4.1, but still has some of these interesting representations that are important for some of the longer S2S, S2D timescale applications. So for the rest of the talk, I'll just be referring to LM 4.0 as LM 4. LM 4.0 went into UFS last October, being the first port, as far as I know, of the GFDL land model outside of the GFDL environments. If you check it out right now, it's functional with CDEPs, with data atmosphere. There's a regression test using Global Soil Wetness Project forcing data with a cold start and restart. It uses a newly developed ESMF Nuopsy driver that checks out the canonical GFDL LM 4.0 GitHub release tag as a submodule. The driver is fairly flexible in its interface so that it's not too difficult to switch out that LM4 version in the future if necessary. So natively in the GFDL FMS environment, model components use the exchange grid, grid of smallest common intersection to communicate. The implicit coupling is handled on it. The surface boundary layer is integrated within that. So a significant portion of the the lift of this project was to port these coupler routines that are used to working implicitly with the tri-diagonal linear solver, though the land is not linear, it's also implicit, into these land-only routines and structures for the NUOPC driver. That's kind of an overview of what this looks like. For the CDEPS data atmosphere configuration, that involves porting the, what did I do? I'm looking for the pointer, there we go. That involves, now I want to go back. I don't think I'm smart enough to use the pointer. So for the CDEPS data atmosphere configuration, this involved porting the surface boundary layer, including the Monin-Oberkopf routine and the relevant portions of the downward elimination sweep in the atmosphere and subsequent communications of fluxes and whatnot before calling the main land model routine. This diagram focuses on the fast physics time steps, but there also is a slow time step land model call. And so that is what's needed. There's also the upward sweep, but that's not needed for data atmosphere, so I'll get to that in a bit. So in addition to the GSWP3 colon restart regression tests, we were also exploring using UFS to launch these century scale data atmosphere simulations. So that slow time step land call that I mentioned checks for alarms that ring to see if there's a vegetation or river property updating to do, and some of those may only be done on monthly time steps or monthly scales. So this allows us to check that everything is functionally correctly in UFS as we would expect. But these longer runs also let us use UFS to generate land restart files natively within UFS and check on that behavior and continue to use the restarts to propagate along. So looking at canopy temperature, overall the behavior of the data atmosphere driven LM4 in UFS compares pretty well with how it behaves in GFDL and with the FMS coupler. There is a slight cooling here. It seems like it's not the difference in LM4, it's a difference in model time interpolation of the CDEPS and the GFDL data atmosphere configuration that were causing the UFS version to be a little colder. So since the data atmosphere configuration has gone into UFS, we've been working on developing the coupled atmosphere LM4 configuration. So we're porting the rest of the relevant routines of the FMS coupler, mainly the upward sweep of the flux up routine and the propagation of the fluxes and states up there. We've tried to preserve as an option the implicit coupling behavior, but as like a model option, but we're focusing on explicit coupling in the driver since that's what the atmosphere and UFS is expecting. And it's, this is fairly typical, but in its current state of development as shown in this abbreviated condensed diagram. Atmosphere runs, it's sending flux in states through the mediator, through CMIPS. That gets received by the LM4 cap. Within the LM4 cap, you have that surface boundary layer with Monin-Oberkopf, and then the main land model executes. So then after that, you have your new surface state, your latent sensible heat fluxes, and in states like temperature, humidity, albedos are sent back to the mediator. And then on the next model time step back to the atmosphere, the CCP radiation has those land albedos and radiative temperatures, and it does what it normally would do to decide if it will use those in RR-TMG calculations. At this stage in development, there are still some things left to integrate, such as some of the surface boundary layer output that would be feeding up into the EDMF scheme. There's also some existing surface data and options in CCPP that are coded for NOAA or NOMP or RUC that are still being employed that we're still sorting out. Generally, our approach has been to try not to just hack in like a new switch for LM4 within the CCPP code, but to try to review the physics and keep everything generalizable in modular. And also, so far, everything I've discussed so far has been with a simple single land type per grid cell, and it's not employed LM4's subgrid vegetation tiling, which I will get to in a second. So with that being said, with all those caveats, I'm going to be brave and show some extremely preliminary plots of our atmosphere land P8-like configuration. So a 24-hour test at C96, showing global surface temperature with cold start and warm start to the land. Among those TBD items I just mentioned, we currently have initialization issue to work through where the radiative influence on the land is not felt on the first time step. So we have this very quick sudden cooling on the first time step compared to NOAA MP atmosphere land P8. But at least this shows that there is some technical functionality to run these coupled 24-hour regression tests. Thank you. I will skip that for time. And we've also been extending to 1 year long free running configurations to stress test the model. Obviously, it quickly goes off the rails and that with that temperature crash in the same way that the regression tests do. But it shows the functionality is there to get into time domains to do coupled spin-up native in UFS or to get to the to S2S timescales and beyond. So like I mentioned before, we're currently implementing LM4's multi-tile treatment. So land grid cell in LM4 can have a lake or a river as part of the grid cell or glacier, and it can also have multiple vegetation types. And each vegetation tile has its own soil treatment, its own canopy and understory energy and water solvers, and can also respond to land use change or fires independently if those are turned on. And each has its own surface boundary layer call and averaging of fluxes and states across the, tiles. And so the question here that we have is how does that compare with what NOAA MP is doing? There's some similarities where both this with the surface boundary layer and land is similar to NOAA MP calling GFS stability. We can use what we do and average the outputs of the surface boundary layer, or we can do what NOAA MP does and have an additional call of that boundary layer or stability routine to get your grid cell level outputs that are needed for the EDMF and propagate to the PBL. Okay, I'll skip that for time. Here's my summary slide. If I have time to wrap up, LM4 is currently in the UFS repo for data atmosphere tests. Since that's been incorporated, we've put in our representations of glaciers, river, and lake model. We have the basic functionality of the coupling with the FV3 atmosphere. Looking ahead, we're looking to soon wrap up that coupling with an eye to ensuring energy and water balance for the land surface. We'll implement that subgrid tiling.
We're at time.
And then look to connect the river routing output to the ocean for fully coupled models. Thank you. Good time, I hope.
Yeah, unfortunately, we don't have time for question. We have to move to the next speaker. Thank you. Our next speaker is Lisa Benson from PSR, talking about the tropical variability in the UFS applications.
Thank you. Can you hear me? Yeah, so I'm going to speak a little bit about tropical variability in the global systems and some of the physics work we've been doing to seek improvements in the tropics. I would like to acknowledge my development partners, John Gilhan at EMC and Luc Girard at RMI Belgium, and also a huge thank you to Maria Gene at PSL for your diagnostic tools and very helpful discussions. You heard about the GFS v17, GEFS v13, and SFS version 1. They will be the first global coupled applications to become operational under the UFS infrastructure. And over the past 5 years, there's been a lot of innovations that have helped improve tropical variability in these systems. One major thing is, of course, coupling to a dynamic ocean model, so the MOM6 coupling. Also improved initialization. And then we have worked quite hard over the past 5 years in advancing model physics from the GFS version 16 to these upcoming global systems. You heard from Kathy's presentation that there's been work in these prototype steps, and I'm sure you're all very well aware of those prototypes at this point. We have summarized all the individual physics updates going into those prototypes on this website here. And I also recommend you see Fenglin Yang's poster out here this week, summarizing a lot of the physics updates in these systems. Today, I thought I'd focus on a very specific physics update and a very specific topic that has to do with moisture sensitivity and convection. So in cumulus convection parameterization, we generally talk about 3 building blocks. So the first is triggering. That's when and where to activate convection. The cloud model itself is the effect of convection on its environment. And then the closure, which is the regulation of the amount of convection by the grid scale variables. So while the closure has some mathematical implication, it can also be thought of as a sort of a practical physical connection. So here I have a very simplified view of the experiments I'm going to present today. The first closure, where here convection amount is regulated by grid scale buoyancy and diagnosed each time step, and I call that experiment prog false. In the second closure, the convection amount is regulated by grid scale buoyancy, but also by moisture flux convergence. And this closure prognostic with some memory and time. So this second closure is used in the GFS v17 and GEFS v13 pre-operational prototypes that you heard about today. But up until recently, we hadn't included it in the SFS prototypes. So I did some work in trying to understand a little bit of the impact on subseasonal forecasting. And if you're interested in the details of this work, there's a publication here at the bottom. So just a quick experiment design. I'm using the beta version that Phil introduced, the SFS beta 0.1, 30 initial conditions between 94 and 2024. 1 year forecast lead times, 11 ensemble members, and I run these at C96, so that's a 100 kilometer grid spacing. So the first thing I look here at is the relationship between moisture flux convergence itself and precipitation in tropical wave bands. And a couple things stand out here. You can see in the ERA 5 to the left, there's a lot more coherence between moisture flux convergence and precip than in the model runs. You can see when we use moisture flux convergence as a source term in the closure formulation, there's a stronger coherence between these two variables, in particular probably in the Kelvin wave band, but also at lower frequencies. Another thing that maybe stands out is it looks like the Kelvin wave band is probably moving a little bit too fast in both our model versions. So the next question I ask is it the low-level moisture flux convergence that leads precipitation in the MJO, or is it because it's raining we have moisture flux convergence? So to answer that question, I looked at the lag longitude regressions and the Homillers of moisture flux convergence and P-rate regressed onto the Rome index. So the black line you see in these plots is the lag equals 0, which is the reference phase ROMI. And negative lags are conditions before, and positive lags are conditions after the Romy index. So the key findings here is that we do see we have this eastward propagation. The MJO propagates eastward from the Indian Ocean, maritime continent into the Pacific. And moisture flux convergence peaks about 2 to 5 days before rainfall, given the same longitude, acting as a precursor to convection. Era 5 has this, let's see if I can figure out this. Can I? Oh, yeah. It has this slightly enhanced positive regression at negative lags over the Western and Central Pacific, suggesting that there's some early moistening ahead of the Indian Ocean maritime continent convection crossing. And this is slightly enhanced in the Prague True experiment compared to the Prague Falls. So I thought I'd pull a little bit on that thread, and I looked at the maritime continent crossing case. In this case, you can see there's quite a wide spread in ensemble members. There's some enhanced amplitude in the Prague True, and that has to do with a few members crossing. But there's also a lot of members that kind of just die off. It doesn't make it past the maritime continent. And if I look at the lag regression homilers here, you can see that in the Era 5, we do have that enhanced moistening over the Central Pacific, which we also see in the Prague True. And I thought maybe it'd be interesting to compare some of the members that do make it across compared to members that don't in these two experiments. So I labeled them here, and I took a closer look at this member 9, where one member passes, and in the Prague Falls, it tends to just kind of lose amplitude. And here you can see quite large differences in this preconditioning in the Central Pacific beforehand of the moisture flux convergence. So let me see if I missed something. Yeah, no, I think this is quite interesting, and the only difference between these two is then in the closure of convection. Here's also just picking out that member 9 from that year to see that the coherence is a lot stronger between low-level moisture flux convergence and precipitation. Still not quite as coherent as we see in the Era 5, and maybe that has also to do with the resolution of the modeling system itself. Another thing I wanted to point out, so as I was doing the study, out of the 30 November initializations that I used, there's only 9 cases that has an observed ROMI index with an amplitude larger than 1. And this is maybe not ideal to study impact of model physics. If the model struggles to initialize the MJO, then it's quite difficult to see the impact of physics. I think, so Juliana Diaz will introduce this idea of a test bed, and this may be part of motivation to that kind of work, that it would be good to identify a test bed of cases that have a large amplitude at initialization, and she will speak in this session as well. Another thing that I wanted to mention is similarly to what Phil saw with the NINU 3.4 index. We see in the MJO comparing the baseline, SFS baseline and SFS beta, that the ensemble spread is much larger also for the MJO and not only for the El Nino. As he said, this is something we are aware of and something that we're trying to tune and improve and maybe understand a little bit better why the MJO was degraded in the beta version compared to the baseline version. Another thing I wanted to briefly point to is the initialization is also very important for MJO prediction. And in preparation for SFS version 1, we found that the MJO amplitude is very sensitive to whether you initialize with UFS replay or if we initialize with the GEFS V12 reanalysis. And upon examining the initial state variables, we found large initial upper level temperature differences. So this plot here, this plot here shows the 200 hectopascal temperature differences, and the GEFS V12 is much colder than the replay, and particularly in early years. Around 2006, the GPS observations started to be assimilated into the GIF's V12 reanalysis, and temperature was warmer, but still much colder than a UFS replay. And an atmosphere that's colder aloft is more statically unstable. We found that following the weak temperature gradient approximation, given the same heating, vertical velocity is then proportional to static stability. And enhanced vertical velocity increases the upper level divergence, leading to an enhancement in the RMM index. Let me just leave it at that, and you can read this paper if you're interested in this work, or come and find me. And I will leave my conclusions up. Thank you.
Unfortunately, we don't have time for questions. Talk to the speakers during the coffee break. If you have any questions, we'll have to move to the next speaker, Kevin Bowers from PSCL, talking about the CAPE simulation in UFS with two different land models.
Thanks, Fanling. Greetings, everyone. In this presentation, we report a few findings from our ongoing work on the ongoing work to address the issue of low CAPE forecast shown up in various UFS applications, particularly in the global medium range forecast using the GFS system. Our colleagues at the GSL published a study in January 2024. They actually showed that the low CAPE forecast is seen in both GFS V15 and GFS V16 forecasts. They have found that both versions of GFS simulate smaller surface latent heat flux and larger surface sensible heat flux standard observations. They attributed this to the slightly drier than observed soil moisture in the GFS that comes from the offline global land surface data simulation system for the land model. It is conceptually straightforward. The issue of low CAPE forecast is closely related to the biases in the representation of atmosphere and land coupling, as realized by coupling of a PBL scheme and the land surface model. As we evolve GFS forward from V16 to V17, we hoped that with the refinement of boundary layer scheme and the replacement of NOAA-LSM by NOAA-MP-LSM, which is more complex than NOAA-LSM, we hoped and expected the issue would be evaluated. It turned out that the issue of low CAPE forecast is still seen in all the GFS V17 prototypes, as illustrated by the next two slides from Wei Zhong. For 3 rounds of GFS initialized on 3 days at 0Z, and compared with the Raven Sound in Tornado Valley over 2 areas surrounded by the red dash and the blue dash. So this is the evaluation of average time series in both area 1 and area 2 to compare with Raven Sound dot and arrow 5, which is cross, and the time series from a RAP/HER analysis. You can see that all the GFS V17 prototypes, together with the V15 and the V16, they all underestimate the CAPE as our forecast time moves along. So you can see that low CAPE behavior, particularly in the summertime, is seen in all the prototypes. By the way, the cases here is a subset of the cases that used by our GSL colleagues in their study I mentioned. Since the accuracy of CAPE forecast is strongly dependent on the accuracy of sensible and latent heat fluxes from the lower boundary conditions for the atmospheric model, which is provided by land surface model. We decided to look into how our forecast, for same physics, here is we just use GFS V17P8 prototype to couple with the different versions of land surface model to understand and to see how the Cape forecast is sensitive to different choices of land surface model. The left column is the initial conditions. You can see that when we coupled with NOAA-MP and with NOAA LSM, and the initial conditions identical from GFS initial conditions or analysis, whatever you call it. And we are using the same land static information to initialize land surface model, both of the models here. So you can see the middle column is the 12 hours. We do not want to look at far. Just look at the first 12 hours. You can see a significant difference in the forecast Cape between the run from NOAA-MP and the run with NOAA. And comparing with the right panel, which is the HER RAP or HER analysis, in this particular case, the results from the coupling with the NOAA LSM is closer to the analysis. But I wanted to emphasize the major difference we see here between the realization of the run with the NOAA-MP and the realization from the coupling with the NOAA LSM. Now, I want to emphasize in passing, such a sensitivity has been seen in all the UFS applications we have hands-on. So this is a kind of worth for us to continue our work, and therefore this report. We can replicate the sensitivity we have seen in the 3D model with a single column model to help us better understand what's behind the differences and the sensitivity we have seen in 3D model. As an example, this is an output from the single column model initialized and forced by the same runs that I showed you in 3D. And this is at Omaha, site of Omaha. And just an illustration of the sensitivity further we have seen. And you can see that the graphic here, you see the blue is the latent heat flux realized from the NOAA-MP, NOAA LSM, and the red is from the realization of NOAA-MP, and the black is arrow 5, and sensible heat is to the right. We don't have clear evidence in any of the reports before, and we cannot say which one is closer to actual fluxes. Also, comparing with the arrow 5, we can see that particularly for the latent heat flux, the sensible heat flux from NOAA-MP is underestimated, while the NOAA LSM overestimate. So for the same side, if you look at the Raven Sound to compare observations, which is in black here, you can see that with that particular realization of sensible heat flux from two land surface models, the GFS boundary layer scheme tends to overmix comparing with the observations, while the realization of the moisture profile from NOAA LSM is closer to observations. The realization from NOAA-MP is significantly drier. So to further understanding the sensitivity in further experiment all of this hierarchical framework for the Cape forecast here, we have identified a numerical issue in one of the models that is NOAA-MP. When we see all the points or all the sites when we have underestimated, comparing with limited observations and limited analysis, we see this numerical issue. Let me illustrate this with the next few couple of slides here. This is surface solar radiation flux from two sites shown in the below panel here. And you can see that for these two sites in northern Oklahoma, there are no clouds. So you can see clear diurnal cycle of solar radiation. When we look at these two sites for latent heat and sensible heat, the top panels is from one side, the low panels is for the other side. You can see that while, because we don't have clouds in solar to affect solar radiation, we expect sensible heat and latent heat fluxes to follow the trend of of daytime solar radiation. But you can see why the sensible heat flux follows quite closely with the solar. The latent heat flux from NOR-MP kind of follow the solar forcing. The realization of latent heat flux from NOR-MP is not. In particular, you can see that at one side you have two peaks here. We cannot explain it as a physical, there isn't any physical reason behind it. So at this moment, we attribute it to a particular numerical behavior from this NOR-MP. Another side even worse, okay? Now this is not just for single color model. We go back to the 3D model with the ISRW. The top panels are the solar radiation. The first and the third rows are solar radiation. The second and the fourth rows are the sensible and the latent heat fluxes from 10 sites, ranging from grassland to forest to croplands. You can see that, that 5 or 6 out of these 10 sites, when you see, you don't see clouds here, you do significant weird behavior associated with what I call the numerical solution from NOR-MP. So these are the points I want you all to take as a take-home message. So we can see that because of two land surface models have two different numerical procedures to solve different energy balance equations of different complexity. There are different realization of sensible heat and latent heat fluxes from these two models. They all contribute significantly to the bias of CAPE. We are now exploring to use more observations to evaluate it, which algorithm actually can give us more accurate or physically sensible resolution. We also show that the NOR-MP LSM has unphysical behavior. This behavior is quite often associated with the situation that the latent heat flux is underestimated. So we are now have a couple of ideas on the testing to get rid of this numerical issue. While doing that, we must recognize the reality here is that we need a lot of observations to evaluate which is the best model we should use. And this raises an important point here that we feel that increasing complexity in representing physical processes without sufficient observations to validate and constrain may not be a straightforward way to reduce model forecast biases. Thank you.
Okay, thank you. I can turn one question. Okay, I will hand say over there. You go ahead to the microphone.
A really quick comment. So we've done similar analysis on a project with Jason Odkin, and we see same issues, and we should talk.
Thank you.
I'd like to point out that the Jason Hodkin issues was a misconfigured model that solved most of the problems.
Was it?
So
Okay.
there's probably using the wrong rate of transfer scheme.
Maybe Michael, do you have a question or not? Okay. Okay, we need to move on to the next speaker. Talked about at the break. If I have more questions, our next speaker is Benjamin Moore, talking about the tropic impacts on weak swing and fall precipitation forecast in California.
Yeah, and everyone hear and see my screen? Yeah, I'll just proceed. Yeah, I'd like to first acknowledge my co-authors and collaborators on this work from NOAA PSL, series, and CPC, for their significant contributions in designing, running, and interpreting the UFS experiments I'm going to be presenting on today. An overarching objective of presenting this work today is to showcase the utility of the nudging approach that we've applied to the UFS for identifying and diagnosing key forecast errors, especially for particular high impact events that may have posed substantial predictability challenges. So we opted, there we go. We opted in this study to focus in detail on two extreme precipitation events during an extremely wet winter of 2022-23. And these events, of course, resulted in high impact flooding, but also helped ameliorate widespread and prolonged drought conditions across the state. So that's kind of background motivation for focusing on this period. And we focused on two, move that out of the way, two particular 15-day periods highlighted here in these time series. The first being the late December through mid-January period, and the latter case being mid-February through early March. And both of these cases were selected because they feature prolonged periods of heavy precipitation within kind of distinct persistent and quasi-stationary anomaly patterns over the North Pacific, highlighted here in this Hofmahler diagram of 500 millibar geopotential height anomalies. And critically, for the purposes of this study, both cases were preceded by enhanced tropical convection associated with the Madden-Julian oscillation propagating over the Indian Ocean, the Maritime Continent, and the Western Tropical Pacific. In addition to that, we had, of course, background La Nina conditions, which also potentially played a role. Looking at operational forecasts for these two cases, weeks 3-4, at the weeks 3-4 lead, we can see that for both cases, these forecasts exhibited substantial errors. For the December and January case, we see that this case is a fairly substantial forecast bust. In that case, the operational ensembles, the GEFs and the ECMWF, clearly failed to predict the extended region of negative geopotential height anomalies associated with a zonal extension of the North Pacific jet stream, which was critical for the development of cyclones and atmospheric rivers along the California coast in that case. For the February-March case, the forecast correctly captured kind of the overall position of this North Pacific blocking ridge here, but exhibited clear errors in the amplitude and structure of the anomaly pattern. Crucially, these forecasts misrepresented the position and structure of the trough over the western U.S., which was a critical ingredient for the occurrence of heavy precipitation in California in that case. All right. Yeah, going to precipitation real quick, the errors in the large-scale flow were consistent with kind of a clear disagreement between the observed precipitation here on the left and the weeks 3-4 precipitation outlooks here. I'm just showing the observed precipitation as a percentile rank in the PRISM climatology. So that's kind of motivation, and that motivates us to oppose this hypothesis. Tropical processes constituted a principal source of errors that hindered subseasonal predictions of extreme precipitation events in California during this winter, 2022-23. So our approach for addressing this hypothesis is to conduct UFS forecast experiments in which errors in the tropics are suppressed by basically nudging prognostic model state variables to the ERA5 reanalysis. We compare these forecasts against a control forecast that's just basically run freely without nudging in order to isolate impacts of the tropical errors and really to establish an upper limit for improvements in subseasonal predictions for these particular events. So yeah, we're using the UFS version HR1. We're running forecasts out to 35 days, including the effects of air-sea coupling. And the forecasts are initialized with the ensemble data assimilation members from ERA5 with plus and minus 12-hour time lagging to generate a total of 30 members for each case. And we select these initialization dates, the 15th of December and the 2nd of February, in order to capture kind of those two 15-day periods of interest in the weeks 3-4 time window. And so we conduct nudging on all prognostic model state variables within a specified tropical region, with the degree of nudging kind of tapered to zero outside of that region to ensure kind of a smooth transition. For each case, we have two tropical nudging experiments, a wide and a narrow experiment, basically to test the sensitivity of the impacts to this nudging approach, or to the width of the nudging region in which we are applying the correction of errors. Yeah, so we compare these nudged forecasts, the wide and narrow, to control forecast, basically, again, run freely without nudging, and then we also use a replay data set where basically the UFS is nudged to ERA5 globally. In practice, this is almost identical to the ERA5 reanalysis. Yeah, so let's jump right into the results of these nudging experiments, starting with the December-January case. Clearly, if we compare the control and the nudge forecasts on the right, and then looking at those in the context of the observed conditions, we see that nudging the tropics vastly improves the forecast representation of the large-scale anomaly pattern for this case, and this is true regardless of the width of the nudging region. So these improvements in the large-scale flow directly correspond to improvements in the precipitation forecast. So shown here on the bottom is the mean absolute error of accumulated precipitation over California for the different forecasts, with plus symbols indicating individual ensemble members, and the brown lines and gray boxes indicating the ensemble mean and the 95% confidence interval around that mean. So clearly, comparing control with the nudge forecast, we see a huge reduction in error. And these improvements in precipitation, in the precipitation forecast for this case, are directly linked with improvements in prediction of landfalling cyclone and atmospheric river activity over the West Coast. So we see that the nudged forecast correctly captures this kind of zonally extensive corridor of anomalous moisture flux, and it also captures the overall persistence of the moisture flux along the West Coast, whereas, of course, the control forecast does not. Looking at the later case, the February-March case, a key finding, first and foremost, is that the nudging results in a significant improvement in the representation of the amplitude and the overall persistence of this blocking ridge here over the eastern North Pacific. However, the improvements in the downstream trough, which again is a kind of a critical physical factor for the occurrence of heavy precipitation in California, those improvements are not so striking. In the wide nudging experiment, we do see a modest improvement. However, in the narrow experiment, yeah, there really is no improvement due to kind of lingering errors in the overall tilt, the implied wave breaking characteristics of the blocking pattern. So accordingly, if we look at the mean absolute error of precipitation down in the lower plot, improvements in the precipitation forecast are in an ensemble mean sense, fairly modest in the wide experiment, and non-existent in the narrow experiment. Moreover, for both experiments, there's substantial ensemble spread. Okay, so these results kind of indicate that even when we impose, for this case, even when we impose perfect conditions in the tropics, there are extratropical processes not strongly constrained by the tropics that are kind of serving as sources of error and uncertainty for this particular event. So to help diagnose those processes, we simply compare nudged ensemble members with low precipitation errors over California to those with high errors in kind of a composite framework. And that's what's kind of highlighted here in this next slide.
You got 2 minutes.
Okay. So here are the weeks 3-4 average conditions. We're looking at composite differences between the bottom 8 and top 8 members in the narrow nudging experiment with respect to the mean absolute error of precipitation in California. On the left, we have absolute vorticity at 200 hectopascals, and on the right, we have 850 hectopascal moisture flux. And also I should point out that the solid contours are the composite field for the low error members, the good members, and the dashed contours are for the high error, say bad members. And a main takeaway here is that the low error members correctly capture this anticyclonic overturning of the absolute vorticity field, or basically Rossby wave breaking on the eastern flank of the ridge, resulting in a deep trough, enhanced moisture flux over Southern California. That of course favors heavy precipitation in Southern California in those members. By contrast, the high error members really exhibit kind of a cyclonic Rossby wave breaking type pattern over the Central Pacific and really fail to capture the pattern that's conducive to precipitation in California. So a main takeaway here is that even if we were to get the tropics right in a case like this, error and uncertainty associated with processes like Rossby wave dynamics and Rossby wave breaking can act to limit the predictability of precipitation. So that brings me to the summary and conclusions for my talk. I'd just like to highlight 4 main points. First, for the cases we considered, suppressing tropical forecast errors substantially reduced mid-latitude circulation errors and improved predictions of the flow patterns that were associated with precipitation in California. But we saw that the impacts in terms of precipitation differed between the 2 cases, In one case, there were large improvements. In the other case, mixed results. So this really highlights the prediction of California precipitation extremes really represents a kind of signal to noise problem that is not dependent on just accurately forecasting predictable large scale signals. The noise can really matter. And in the February through March case, the noise was kind of manifested by Rossby wave dynamics and Rossby wave breaking. And lastly, just like to again emphasize that this nudging approach is an effective tool for identifying and diagnosing principal sources of error in UFS forecasts. So with that, I'll conclude. Thank you.
Yes, thank you, Benjamin. We have to move on to the next speaker. Daniel, I say Anson, I have to say it right, and the evaluation of the land answer coupling and in the UFS using Met Plus.
Thank you. I'll just say thanks for having me while we get the slides queued up here. And I just want to acknowledge our collaborators from SUNY Albany and the University of Wisconsin. And I guess while I have a minute, I'll encourage you to search the agenda for Met Plus. There's at least 4 additional opportunities tomorrow, 2 posters and 2 talks that I'm aware of, if you're interested in learning more about Met Plus and its applications. So today I'm going to talk about some new capabilities for land-atmosphere coupling and evaluating that in UFS prototypes using Met Plus. So a little bit about what Met Plus is. It's a verification framework, spans lots of different scales, both temporally and spatially. This is sort of just a high-level overview diagram we'll talk a little bit more about on the next slide. It's really has a really large user base worldwide. Lots of different applications highlighted here, from tropical cyclones to cryosphere, sea ice, data assimilation, space weather, and other areas, and we're certainly expanding. We have a big community support network, and we use GitHub discussions to engage with the community and make improvements and help identify issues that we might need to resolve. It contains a lot of use cases for easy spin-up. We'll talk a little bit about those in a minute. And recently we released a package on CondaForge, so you can install Met Plus that way if you prefer. So a little bit about the Met Plus components, referring to the diagram from the previous slide. We have a suite of Python wrappers represented by the black arrows in this diagram, which is essentially a low-level workflow for controlling how each component interacts with one another. We have a set of analysis tools for advanced analysis, including MetViewer, MetExpress. And we also have some Python components, MetData.io, MetCalcPy, and MetPlotPy. We'll cover a little bit about MetCalcPy in this talk today. And then sort of underpinning all of this is Met, and that's in the upper left corner, which is a suite of statistical and diagnostic tools. So here's a wire diagram of all of the capabilities that exist within Met. So again, it's a suite of statistical and diagnostic tools, but it also does lots of other things like reformatting, data interrogation and querying, statistical tools, as well as some tools for analysis. We support grid-to-grid, grid-to-point statistics, ensemble statistics, spatial methods, and also methods specific for tropical cyclones. So as I mentioned, Met Plus comes with a suite of use cases, and we're going to talk about use cases that we have recently included for land atmosphere, is what this should say. We'll be updating that in the next release from land surface. But the use cases contain example workflows using real data that people have submitted to apply verification techniques that folks in the community might want to leverage for their applications. So we're going to talk about these 3 use cases and some upcoming capabilities as well. So the first use case I wanted to discuss was evaluating the terrestrial coupling index. So what this use case is doing is taking FluxNet observations and comparing with some CESM model data. We have a subset from 1979 and 1983, and some astute observers might note that FluxNet might not exist during that time period, but this is more intended to be a demonstration of the capability for those of you that have model data that would overlap with FluxNet. The TCI calculation is actually available through MetCalcPy's programming interface, API. So if you wanted to interface directly with the calculation in Python, you can do that. The next use case is convective triggering potential and humidity index, or CTP-HI. These are using Paul Durmeyer's metrics for humidity index and convective triggering potential to assess the convective coupling during wet and dry phases. So the data that comes with this use case are some radiosonde upper air observations from GDAS data stream, which is available via the RDA and other archives. We're using UFS prototype forecast profiles, and we've sort of implemented this to be computationally efficient because it does involve some partial calculations for CTP. Just like the terrestrial coupling index, the CTP, that should say CTP, and HI calculations are available through the MetCalcPy API, and if folks are welcome to interface directly with them in Python. Here we've implemented them with Python embedding, which essentially calls Python, computes the metrics, and hands them off to the Met statistical tools to compute the output statistics. The graphic here is using the matched forecast and observation pairs, so the GDAS observations and the UFS forecast pairs to evaluate the wet and dry phase space depending on what quadrant of the lower panel that you are in. The third use case that we've included recently is using International Soil Moisture Network observations, ISMN. So we have capability for global ISMN observations, all of the subnetworks that are part of that. And here we're showing an example using those observations to evaluate UFS prototype forecast data, again, the same UFS forecast from the CTP-HI use case. So what you can do here is we have this plotting capability on the end as well to help look at soil moisture and soil temperature variability. Here I'm showing soil moisture bias across the CONUS. And I want to note here that this use case does not need Python embedding. The ISMN observation data are directly supported in ASCII to NC, which is a pre-processing tool available in MET. So you can point that tool directly at a directory of observations from ISMN to process them for use case. There's no calculations here, no diagnosis being computed, but we hope to use these data a little more broadly. I'll just cover a few upcoming capabilities, and then we'll have a few minutes for questions. So one capability we're working on here is developing model comparison scorecards for land atmosphere use cases. Here's an example which includes the Bowen ratio, which is a land atmosphere metric looking at, I believe, soil moisture here. And it allows a quick comparison between model versions. This use case with the scorecard here, you can see in the title, is going to leverage a New York State Mesonet standard and flux site data for near surface weather, soil states, surface fluxes, and other variables. So we saw an example of the scorecard earlier in this session as well, but we're hoping that we can expand these into the land atmosphere verification realm. And finally, two additional upcoming capabilities looking at soil moisture temperature coupling from these GRL papers and vegetation atmosphere coupling as well. So be looking for 2 or 3 additional use cases that help demonstrate these capabilities and using real data and workflows to be applied for your applications. The third thing here, bivariate mutual information theory. I can't recall who we're working on with that, but that's going to be the third use case. And then I also want to highlight, too, that we're coordinating with NOAA to help implement these land atmosphere verification capabilities in an upcoming EVS release. So that's all I had. I wanted to leave a few minutes for questions in case folks had any comments or clarifications they needed answered. But thank you for having me. I appreciate it.
Next time we do have time for a couple of questions.
I'll ask you a quick question. So the EVS, or like preparing for, say, something to do in real time, these land data sets are usually like very difficult to get and have a high degree of latency. Is there any plan for that?
Yeah, we have had some discussions with folks at NOAA about prioritizing the data sets that we would need access to, so they can start working on their end at ingesting them. And we've also sort of tried to think about how to aggregate in the time dimension, because a lot of these things vary over long periods, to be able to evaluate the effects. So we're looking at both of those to try and address those.
Talk by week one and talk about the UIFCW forecast system on cloud.
Wei Huang, I work at Epic from ATX Technology, and this work is done with Neil Button at EMC. So most of people here know what is seasonal forecast. So that's doing kind of longer time forecast for to bridge the weather and the climate. So that's for us, the purpose for us at Epic is we wanted to work with EMC to explore another option. Instead of running on the NOAA on-prem machine, we want to run it on different platforms. So as we say, the key features of the SLFF is extended range. So it's a longer range, and it means that you're going to consume more computer resource. Also here is a coupled model, that means more resources you need. And in some forecast, that means you're going to double or triple or even more of the computer resource. So as I said, Epic works with the NOAA SF team and many others for this purpose. So first we work with NOAA Parallel Works. So those people to help us and work with them to create clusters on AWS. Then we can start the experiment. And later on, we will select different different clusters or different chips to invest how we can run it efficiently, not just run, but run it efficiently. And the first we do is say we add new the global workflow module files to the spec stack into on AWS, so we can make the global workflow run on AWS. Then we work with, that's the time we work with the SFS team to have their initial conditions to move to cloud, and certainly we need to learn how to run the SF model. So as I said, the SFS global workflow has many tasks. So for example, we need to stage the initial condition, we need to do the model forecast, then we have to process the forecast. They have components like atmosphere, ocean, ice. So these components we need to process this. But every of these tasks need to have a different request for the computer resource. For example, model forecast, you need more resources, it means you need more nodes or more computer processors. For the atmosphere, ocean, ice, the products part, you need less. So for example, atmosphere and those ocean ice products, usually they only need 24 processors. So in that sense, that means we do not want to use the same large node for general purpose. We want to use different nodes for different purpose. So here, as I said, the forecast, we will use a larger fat node. Then we can make it run faster, efficiently. And for those small tasks, we want to run a thin or like a lean node. So in that sense, we do not want to pay much. So that is the purpose. So as I said, so SFS team provide us the initial conditions. That initial conditions previously stored on the on-prem machines. Then we transfer this initial condition from a normal machine to the cloud. They have very good tools to use. That's the AWS CLI tools that can use that you can transfer actually pretty easily. So then we certainly after we've done that one, we can use the a script generator workflow, this script to generate the experiment. And then after we generate that one, we can use the cron tab to run the SFS model there. So certainly after you run, if you check the status, all the statistics, you will see it will tell you each step how it runs, how it ends. Here we can see we use 3 members, so that we can see all the members run, finish the succeed, and we can see also the atmosphere parts succeeded for each steps. Certainly there is one very long list, so I only list the top parts of the statistics. So to run on AWS, it's different to what you run on the on-prem machines, because on-prem machines you have a kind of GUs. That means you have a bulk, a bulk size of GPU. You can the CPU time you can use. But on AWS, that means everything you do, you need to pay. So for example, you do a controller, and you have we have a controller. We use a very small node to do the controller. You only pay 36 cents per hour. Also, you need to understand that you have a lustre you need to pay. Here, for example, we have, I think it's 1 tera lustre. You only pay 23 cents an hour. So you need to remember everything you need to pay. So for example, we run a very small, let's see, go back a little bit. So for example, if we run a case with, for example, here we have a compute, for a computer, for example, we have the price of $4.3 per hour. For the process, we use a small node, I say it's $2.16 per hour. So if you have a case like this one, you can have the cost added together. So you have to add them together, you have the total cost. So also for storage, if you store your data on the S3 bucket, so that's a price you're going to pay. So if you store there for a month of data there, let's say, for example, you save, if you store 1 terabyte of data on S3 bucket, for each month you're going to pay $21. And also same here, so this is the lustre. If you use the lustre, you have to pay the price there. So for each hour, for a 12 terabyte lustre file, that cost is $23. Also, here, this is we do 2 cases. So one is the C96 case. So that's kind of the size of the files, the initial. That's the size of the initial conditions. That's when you run, you need this much workspace to work with. So finally, they will generate the final product. Will have this much of the data there. So you need to keep in mind have this kind of data there. And this is the cost. So the cost will be say, if you use a different, this is a different chips. So this one have 24 processors. This one means you have 96 processors, and this one something like a 5 nodes, so that the price are different. So that's the cost. For example, if you run 1 month, that's the cost of running 1 month of the cost. This project you run 1 year, it will cost you this much. But what we can see with a better choice of a node and the layout, you're going to you can kind of save quite an amount of money there. So this is the C192 case. So that's the kind of size of the initial condition. That's the size of the running, when you're running, the working disk space you need, and that's the final product size of the files you have. And say like that's the kind of the statics for each components of the model. So that's how we kind of add together the cost. That's one more test for that. So we use this test like more. Like if you are running for example, if you run C192 case for a year with 10 members, that means that this is a kind of big number you have to keep in mind. So if you want to run there. And we have some load balance test. Load balance kind of have some impacts, but not that. They have some not that. Probably like it's kind of pretty significant here. So if you run like different, like for example, this is a CIS MPI task. So if you use use a proper kind of the proper task assignment, you're going to save some money there. And this is kind of more of the cost we made. So like in summary, so when we run it, we not just make it run it, we wanted to figure out how we can choose different types of chips to run it more efficiently. And we also figure out adjust the load balance can have some, may not have big impact on the performance. And certainly we want to work with the people if you are interested in to switch to AWS, to do tests. So we can help. That's all I have. Yeah, thank you.
Probably we can entertain one question.
My experience running on the cloud is that the computational time is comparable to HPC, but the communication and the I/O is slower. Have you looked at the timings in your different tests and compare it to the HPC?
We haven't explicitly tested on that one because we didn't separate those two because the communication and the computing basically we treat it as a model cost, so we haven't done that part. So what we focus on is the computation. We want to use a larger node to reduce the computation time. For the process part, because you use it doesn't use that much processors. We want to use a small node, then we don't want to pay the big price because the larger the node, is more expensive.
I think we should move on to the next speaker on the list. Juliana Diaz from PSL talk about the MGO test bed that has been mentioned earlier.
All right. Nobody's overloaded yet, right? You're ready for one more presentation. So thank you for still being here, and thank you to the organizers for putting this together. So what I'm going to talk about today is an initial development of a MJO testbed to support UFS global applications. And this is a joint work with Maria Gannett, Lisa Bankston, and Christina Stan. They are all here, so come talk to us if you like what you see. Here, I don't think I need to really go into the woods of what the Madden-Julian oscillation is, except to say that it is an intraseasonal mode of variability in the tropics that modulates weather in the tropics, but also outside the tropics. And because of that, we think of it as an important source of subseasonal predictability that we would really, really, really like our prediction systems to leverage on. And even though the MJO has been notoriously difficult to predict and even to just simulate in a global model, there has been some progress over the last 10 years, including progress across UFS global applications. And I'm going to illustrate this with a paper by Wang et al. In 2025. And I'm choosing this paper in particular for two reasons. The first reason is that they have some nice plots. And the second reason is that I'm trying to set you up for something I'm going to say in a minute. So they were looking in this figure at composites of MJOs that were initialized during phase 2 and 3. And then they compared this to the same cases in UFS prototype 7 and prototype 8, where you see some improvement in MJO prediction that actually carries out to improved prediction skill. And as you've seen from Lisa's presentation, this overall improvement in tropical variability in the UFS is something that has been noted over the past, say, 5 years. These authors in particular looked at MJO teleconnections, and they did that by looking at this metric of MJO teleconnections called stripes that you're looking at here on the top, darker colors indicating regions where that are more sensitive to the MJO. And then if you look at biases in P7 and P8, you see some improvement, particularly over the North Pacific. But obviously, you still see a lot of biases everywhere. And if you're paying attention to my previous slide, you saw that there was also some issues with MJO evolution and amplitude, which takes me to the second reason why I picked this paper in particular, which is to highlight the time lag between when P7 and P8 were produced and this paper came out. And from a diagnostic standpoint, like mine, it makes total sense. It takes time to do this analysis. It takes time to go through the peer review process. But from the standpoint of a model developer, you're looking at an evaluation of something that is outdated, that is not as useful as it would have been a few years before. And this is just a common issue with process level evaluations, but there are some challenges that are particular to the MJO. In particular, if we're thinking of integrating MJO evaluations with model development, we would have to adapt traditional diagnostics because they often rely on a very long record of MJO events. We would have to deal with the fact that we can't really calculate a model lead-dependent climatology because we will probably not have a full reforecast. And then finally, not only MJO process level diagnostics are very time consuming, but to go then a step further and translate them into an improved prediction really relies on this tight collaboration between modelers and domain expertise. And that's what we hope that a testbed can help out with. If we can agree on a set of MJO events, maybe we can overcome some of these barriers. And that was a very long introduction to what we actually have done so far, which is to list MJO events. We did this by looking at a OLR-based index that we applied to ERA5. If you're curious about the use of ERA5 to look at the MJO over that earlier portion of the record, I would refer you to this paper here. In our website, you can look at events that by phase, and we also have a plotting tool where you can compare MJO evolution across indices, if that's something that you're interested in. And here I'm listing MJO events that occurred between December and February over the entire ERA5 record. And that speaks to the potential value of extending reforecasts as far as we can if we're really interested in MJO predictions and predictability. but that's not our reality. In reforecast, we typically have only 20 years. If, for example, I was interested in that phase 2 and 3 initialization, and I wanted to compare GAFS version 12 with GAFS version 13 that was discussed earlier today, we would have only 8 cases. And we counted this several months ago. Right now, it would be either 0 if you're not going to use those reforecasts, or a little bit more than 8. But 8 also seems like a good place to start if we're thinking of an MJO testbed. So we decided to go ahead and explore the idea of looking at differences in MJO prediction between GAFS version 12 and 13 as a step towards our MJO testbed. So here, the first thing we looked at are phase diagrams of MJO using ROMI, similar type of figure that you've seen in Lisa's talk, where consistent with what we see in the literature, we see an improvement in MJO evolution. And you've seen Lisa's talk. A lot of this has been attributed to adding an ocean component, updated parameterizations related to cloud and convections, but also initial conditions might be important, as you've seen already today. And if we really want to understand why these changes have happened, a testbed might be what we are looking for, as Lisa also pointed out earlier today. We are also interested in impacts of the MJO outside the tropics in this very limited data space. So what we did here is to look at hit rates averaged over those 8 cases. I might not have mentioned we have 11 ensemble members for each of them. Hit rates decay, as you would expect, in the mid-latitudes. And if we look at version 12, you see something similar, except that I highlighted where differences are significant, and in particular where GAFS version 13 is doing better. And maybe your eyes have been drawn to the same feature that mine were when I first looked at this, but you can see it a little bit better in the difference, where there's potentially a signal of the MJO tropospheric teleconnection pathway in this enhanced skill, suggesting that maybe 8 cases is enough. I would probably find this more robust if I had more events, or maybe we could look at other phases of the MJO as well. Which takes me to the last point I want to make, and now this is related to what Ben showed you a few talks ago, which is how much should we expect from an MJO from an improved MJO in our predictions in the mid-latitudes. And to partially address this question, we did some tropical nudging on those 8 cases that you've seen already. Those were the hit rates that you already saw. If we nudge the tropics, we see some improvement at longer lead times that, again, potentially resemble the pathway of the MJO, suggesting that improvements in the tropics could lead to better predictions outside the tropics. And just to summarize quickly, we have this list of MJO events in our webpage. Looking at 8 of them, we were able to show that there is an improvement in the MJO and MJO teleconnections between GAFS version 12 and 13, and tropical nudging suggests that we can still do a little bit better. And more importantly, as you've seen, we are just beginning to think of how to build this testbed, and we really want it to be successful. For it to be successful, we need feedback. So if you are interested in MJO in any shape or form, please come talk to us after this. Thank you.
I think we have time for 1 or 2 questions.
We haven't for this, but I think it's an idea. We probably have dynamo cases in this list because those events were strong. So yeah, we haven't, but it is a place where you would have even more observations to evaluate against. Yeah.
Any question online? May I ask? Also from the earlier talk about the nudging, for the process study, can we say further narrow down the signal comes from on-pole region, or you have to nudge the entire topics or the MGO connection there?
So we have not explored nudging just the Indo-Pacific Ocean. That has been done before by CMWF people. It is the Indo-Pacific region that will lead to that, but we haven't done it.
No more questions. We thank all the speakers today. And also thank Aaron Jones for monitoring time, Mike Bargy for monitoring speed online, and also technician at the backside. Thank you, everyone.